Assalamu alaikum. Continuing with the design examples of finite state machines, today we'll be covering instruction dispatcher as another example of finite state machine. Let's first understand the working of an instruction dispatcher and how it fits in our overall system. Then we'll move on to the design using FSM. An instruction dispatcher is a unit that's placed right next to the program memory. Program memory is the part of your system that holds all the instructions. That's what the program memory has. If we assume for the sake of our example that we have a 32-bit wide program memory, it means that we will get a 32-bit wide data at every clock cycle. This data will be fetched to the instruction dispatcher, which essentially will understand the instruction and send it to the decode unit for further processing. Now, if we assume that we had a fixed length instruction, that's for a 32-bit wide system or 32-bit wide program memory, we'll always be getting a 32-bit instruction, then the work of instruction dispatcher is nothing. So we can say that for a fixed length instruction system, for a system that has a fixed length instruction, we can simply discard the instruction dispatcher. But that is not the case, especially in modern day ARM processors, ARM being advanced RISC machines. Though the system is 32-bit wide, but the instructions can be of multiple lengths, meaning specifically talking about ARM, we can get three different types of instructions. One 32-bit long instruction, we can have a 16-bit instruction, or we can even have a 8-bit instruction. That means that the 32-bit wide data that we are getting, it may or may not be a single instruction. That's where the instruction dispatcher comes into play. The instruction dispatcher has to analyze this instruction, has to analyze the 32-bit data coming into it, and on the basis of that 32-bit data, it has to understand if it's a 32-bit long instruction, it's a 16-bit instruction, or it's a 8-bit instruction, so that accordingly set number of bits can be sent to the decode unit for processing. Though ARM has three types of instructions, but we'll be talking about only two types of instructions for our design. We'll be assuming that we have a 32-bit wide program memory, and the instruction dispatcher which we'll be designing gets a 32-bit word from the program memory. The two types of instructions that we'll be dealing with will be 16-bit wide instruction and 32-bit wide instruction. In order to understand or in order to make sure that the instruction dispatcher understands which instruction is currently being processed, the least significant bit will be of use. The least significant bit of these 32 bits will let us know if this is a short instruction or a long instruction. If in the least significant bit of this 32-bit bit word we get 0, it means that we are dealing with a short instruction of 16 bits. And if we get 1 at that least significant bit, it means that the whole 32-bit wide data is to be considered as a single instruction and it has to be dispatched. The general understanding of an instruction dispatcher is that it will either send a 32-bit instruction to be processed, or it will somehow send only 16 bits that have to be processed subsequently. In our design, we'll be designing both parts, the data path and the controller. The controller will be designed using FSM, whereas the data path will be controlled using the signals coming from the FSM. That was the logic that we have already understood. The same logic was replicated when we designed a 4x5. Before jumping into the design, let's just see the overall architecture and the placement of instruction dispatcher in our system. By the system, I mean it's similar to your processing system. Any instruction set processor that utilizes instructions to execute its data, there we can have an instruction dispatcher. So coming to the very basic processor design, we have a program memory that holds all the instructions. We have a program counter. The main aim of program counter is essentially to inform the next instruction, or to hold the address of the next instruction that's going to be executed. Because we are dealing with a very simplistic model of an ASIP, so for that matter we have only considered a counter based, a simple counter as a program counter. We haven't considered a number of different kind of instructions. Then we'll have this is the basic architecture that our system already has. Now the additional parts that our design will hold are the instruction dispatcher, the design of the instruction dispatcher, that's going to be our data path, and a controller that will be linking both items, that will be linking the program memory, that will also be linking the data path, and subsequently the movement of data in the data path will be controlled by the control signals or the control signals generated by the controller. A little more insight into this whole mechanism, and then we can start designing our architecture. When we say that our system or our program memory can hold two type of instructions, a short instruction of 16 bits and a long instruction of 32 bits, what does it mean for our program memory, or the contents of the program memory? Now we can assume a few instructions. We can say that in the first location we have a long instruction. That means a 32-bit wide instruction is already placed in location number 0. Location number 1 can hold two short instructions. That's easy to understand, because a single location is of 32-bit wide and a single short instruction is of 16 bits, so we can easily hold two short instructions. But there are other mechanisms as well. There is a possibility that we had a short instruction in the least significant portion of this location number 2, and the rest of the 16 bits belong to the long instruction and the 16 bits of the long instruction. Where will the remaining instructions of this long instruction be placed? They will be placed at the least significant bit of the next subsequent location. So this will be containing the 16 high bits. Now the next possibility is that we can have a short instruction here, we may have a long instruction here. It totally depends. So because of this kind of packing or this kind of content writing in the program memory, the mechanism through which the instruction dispatcher works, it becomes very critical. Because for the sake of understanding, we say that we start off with PC is equal to 0, so the first instruction that's going to be executed is long instruction. That means that we need to pick this long instruction and send this to the decode unit for further processing. At the same time, we'll increment this counter so that the next instruction should be available to us. But while we get the next instruction or the address for the next instruction, the instruction dispatcher gets this information that the next instruction to be executed is a short instruction. So it will only pick these 16 bits and send these 16 bits for processing. Unfortunately, we have only executed on the first instruction or the first part of the instruction right now. The remaining 16 bits are still to be worked upon. So we will not be incrementing this program counter. We need to first process on these 16 bits. Once this is done, then we will move on to the second address. Understood? But in case of this second address, when we move on to 2, this implementation of short instruction is easy to understand. But what happens with the low part of the long instruction? This cannot be executed in the next clock cycle. It has to wait for the higher part of the long instruction, so that as a whole we can get 16 bits from low and 16 bits of high. As a combined unit, we get a long instruction. So the instruction dispatcher has to keep track of all this information. It has to keep track of when and where the instructions have to be moved, which data of this 32-bit instruction is acting as a whole 32-bit instruction, as a long instruction, or it's acting as a short instruction. So the instruction dispatcher plays a very important role in the implementation of variable length instructions. Now, in order to design a system, our first information will be that we'll have two sets of registers. These are going to be physical registers, so we should write clock here. These will be representing IR, let's say we can say it as IR0, we can call it as IR1. This will be IR0's low bits or least significant bits, IR0's most significant bits, IR1's low significant, and IR1's most significant bits. So these are essentially the instruction registers. These registers will contain the instruction that is going to be executed next. The data being provided to the instruction will be fetched from the program memory, and the data being provided to the decoder for further processing will be provided by the second instruction register by the name of IR1. This as a whole, which we are going to design in a short while, this as a whole will be our instruction dispatcher. Now let's just start off with the very first iteration. When the system starts, both IR0 and IR1 are empty. So at the first clock cycle, we need to read the data, and when the data is read, the program memory, the contents of 32-bit byte content, the instruction that's currently being read from the program memory, is going to be written into IR0. At the same time, the data coming from IR0 has to be written into IR1. This is going to take place at the first clock cycle. In the second clock cycle, if after this operation of first clock cycle, we can say that IR0 is filled, but IR1 is still empty. So in the second clock cycle, we'll again read data from the program memory. So the data from program memory will be written to IR0, and the data from IR0 will be written to IR1. So after two successive reads, we'll have the data successfully available in IR1 and IR2. IR1 will be holding the data the first instruction that is to be executed, and IR0 will be holding the next instruction that's going to be executed. Now the problem starts here, that if we start reading the content of IR1, we can get two possibilities. We can either have a long instruction, we can either have a short instruction. Who told us that it can be a long instruction or a short instruction? It was very easy. The 0th bit of IR1 will tell us that either it's a long instruction or a short instruction. So if we assume that for the sake of understanding, if we assume that the first instruction that's to be executed is a long instruction, then the subsequent step becomes very easy. What's going to happen here if we get a long instruction is that the data available in IR1 is to be forwarded. By forwarding, I mean the whole 32-bit has to be sent to a decoder. It has to be forwarded to decoder. But in case of a short instruction, things will become a little difficult. Let's just complete the long instruction, then we'll move on to the short instruction. If somehow we got the long instruction, the IR1 data will be forwarded to the decoder. At the same time, the data from IR0 is going to be saved into IR1. Now that we have a 32-bit space available to us, we can call upon the next instruction, and that next instruction can be saved into the next instruction coming from PM can be saved into IR0, because the data from IR0 is now saved into IR0 and the data from IR1 has been forwarded for further processing. This is the easier case of the two. Now coming to the short instruction. Now considering the case of short instruction, the work of instruction dispatcher increases immensely. Now we'll be forwarding IR1, the lower part of IR1 will be forwarded to the decoder. That means the only 16 bits are going to be forwarded from IR1. If we come here, the data available in IR1 lower part will be forwarded. It means that this, for our reckoning, is empty. Now the next steps are going to be crucial. We'll be moving IR1, the higher part of IR1 will be moved to the lower part of IR1. We are left with this space. The higher part of IR1 is empty. We'll move IR0, the lower part of IR0, to the higher part of IR1, and we'll move the higher part of IR0 to the lower part of IR0. Meaning, if I write here, it means that IR1, the higher bits of IR1 will be moved to the lower bits of IR1. The lower bits of IR0 will be moved to higher bits of IR1. Similarly, the higher bits of IR0 will be placed into lower bits of IR0. And the only place that will be empty right now will be the higher bits of IR0 will be empty. At this point, when we have executed only a single short instruction, we cannot call upon the next instruction from the program memory because only 16 bits are currently available that can be written. Whereas the bus that's carrying data from the program memory to this register is of 32-bit byte. It means that at every subsequent read we'll always get 32-bit instruction. A 32-bit data will always be fetched from the program memory, and as we don't have 32 bits available in IR0 or IR1, we cannot save this instruction. That means no read from the program memory will take place when a single short instruction has arrived. Moving forward, we say that after the short instruction, we get again we can have two possibilities. We can either have a short instruction or we can have a long instruction. This has been considered that we have at present IR0, the higher bit of IR0 is currently empty. We are saying that we have executed a single short instruction, and now it's time to see that the next instruction, is it a long instruction or is it a short instruction. So we'll try to sort out both of them. Let's consider the case of short instruction right now. It's an easier because we have already understood the basic mechanism in the previous operation. The operation right now will become rather more easy. So here again, the lower part of IR1 will be sent to the decoder, whereas the higher part of IR1 will be saved into the lower part of IR1. The lower part of IR0 will be fetched into the higher part of IR1. But because IR0H was already empty, we cannot move the content of IR0H to IR0L. Thus we are left with IR0H was empty and IR0 low, both are empty. Now that we have a slot of 32-bit available to us, we'll simply call upon program memory, and the data from program memory will be saved into IR0. A whole 32-bit byte data coming from program memory will be saved into a 30-bit register of IR0. This is the case when two short instructions have been processed one after another. Now coming to the case where though in the previous operation we executed a short instruction, but the next time around we are left with a long instruction. So in case of a long instruction, the first operation is very easy. The whole of IR10 will be sent to the decoder. Now if the whole of IR1 has been sent to the decoder, we are only left with 16 bits of data in this whole of 2 registers. How's that? Because we are saying that we have 32-bit data, we will pick this whole register, we'll send this 32-bit byte out. This because this data has been executed upon, it means that this data is no more useful to me. It's empty. For our reckoning, it's empty. The only viable data that is left is in IR0 low. In such a case, the data available in IR0 low will be directly fetched into IR1 low. Now we are left with 24 bits that are empty right now. In that case, because we have not 24, rather 48. Because 48 is greater than 32, and it means that we can fetch a new instruction. The new instruction that's being fetched from program memory will be split into 2 parts. The lower part will be saved into IR0H and the higher part will be saved into IR0L. It's been done so that the consistency, the overall behavior of the actual data being saved into program memory remains the same. Meaning, I'll just represent this here as again, the data available in IR0 low will be saved into IR1 low. The data from PML, that is the lower part of program memory, will be saved into the higher part of IR1H, and the data from PML, the higher part of program memory, will be saved into IR0 low. Because we say that IR1 will always contain the instruction that is to be executed next. IR0 will contain the instruction that's going to be executed in the next clock cycle. In that manner, the most significant, the most recent data, the least significant bit of the instruction which fetched should be placed into IR1, because IR1 is empty. So we first fill out IR1, and the remaining bits that are left in the PM or the instruction that was fetched from the PM are saved into IR0. Let's just recap the possible steps that can be executed for variable length instruction dispatcher. We started off our proceedings with the first read operation at 0, where IR0, the content of IR0 was written into content of IR1, and IR instruction fetched from the program memory was written into IR0. In the next iteration, another read operation was executed, meaning that data of IR0 was written into data of IR1, and instruction was fetched into IR0. Initially both were empty, and after execution of 0th iteration of the first read, only IR1 was empty. So after both successive reads, both IR0 and IR1 contain instructions. There were 2 possibilities from here on, that we can either get a long instruction or we may get a short instruction. So in case of a long instruction, the data from IR1 was fetched to the decoder, whereas for data from IR0 was fetched into IR1, and the data from instruction was fetched into IR0. Interestingly, the last 2 steps are same as the ones which we took at read number 2. This means that if we consider them as states, it means that whenever a long instruction occurs, it's similar to state that was occurring at read number 2. In case of a short instruction, IR0 low was sent to the decoder, IR1 high was saved into IR1 low, and IR0 low was saved into IR1 high, and finally IR0 high was saved into IR1 low, leaving us with one entity short, that was IR0 high, was empty now. After the short instruction, there were again two possibilities, that we could either get a long instruction again, or we might have received a short instruction. In case of a long instruction, the initial setup was similar to the one which we did in case of a long instruction, that is IR1 gets to the decoder, whereas IR0 low gets to IR1 low. Now why is that? Because we don't have data in IR0H, so it makes no sense that we place IR0H into IR0H. So what comes into IR1H, that is the lower part of instruction was fetched into the upper part of IR1. Similarly, the higher part of instruction was fetched into lower part of IR0. Whenever we say that an instruction has been fetched, it means that we have successfully executed a read operation from the program memory. After the execution of this long instruction, we are again left with IR0 high as empty. So if we again start comparing it similar to the short instruction that we or the setup that was fetched after execution of a short instruction, it's similar to that once a long instruction is executed right after a short instruction. Now coming to the short instruction, this is the second short instruction that's being executed by when one short instruction has already executed. So in this manner, IR1 low will be fetched out to decoder, and IR1 high will now come to IR1 low, and IR0 low will come to IR1 high. And now that we are left with IR0 low and IR0H both as empty, we will simply pick instruction and place it in IR0. This again, if we start comparing, this again seems similar to the long instruction, where we have 32-bit data available, 32-bit space available to us, and we simply pick the 32-bit sent by the program memory and save them into IR0. Though they may seem similar, but every subsequent operation requires different type of execution, or it means different data handling. This is apparently this is all possible cases, because after short we can either have long instruction or short instruction that's already been handled, and similarly after long instruction we can either have short instruction or long instruction that's already handled. So these are the possible scenarios that can occur in our instruction dispatcher. Now coming to the design, I'll start off with the very basic things that are required, and we'll build on that. Initially we'll require a multiplexer right after IR1. The aim of this multiplexer is to send either a 16-bit data from IR1 or a 32-bit data. In case of a short instruction, we are only passing on IR1L. So in that case, only 16 bits of IR1 will be passed, and the remaining 16 shall be 0. Whereas in case a long instruction is being processed, the whole content of IR1 will be forwarded. So we'll have a select, let's say we call it that select 0. This is the select signal that will be controlling which instruction is currently being executed or which instruction is going to be executed. In similar manner, we'll be requiring muxes for every sub-register available in our design. Meaning, coming here to IR1's lower part, we'll be requiring a mux here. And looking at this structure, we can see that there are only two possibilities. Either we can get IR1 higher part, which we saw occurring when a short instruction was being processed, or we'll get IR0's lower part. That is going to occur when a long instruction is being processed. So we'll again have a select one. In case of IR1H, here we have multiple options available to us. The first option is IR0 slow bits. That was occurring when a short instruction was taking place. We can see that from the very first short instruction that the content of IR0L is being saved into IR1H. So we'll be requiring IR0L to be saved into IR1H. Second possibility is that we simply save IR0 into IR1. In that case, the higher part will be saved into the higher part and the lower part will be saved into the lower part. Because we're only dealing with the higher aspect, so we'll have IR0's higher bits. The third possibility occurred when we had a long instruction right after the short instruction, where the content of instruction, the lower bits of instruction was saved into IR1H. So we'll have another input signal here and we'll have instructions lower bit saved, and we'll have 0, 1, 2. So another select line. Now coming to IR0, the possibilities again are numerous. The first possibility can be that we can either save the content of IR0H, or we can save the lower part of instruction, or we can save the higher part of instruction. Again, if I quickly go through them, the IR0H was being occurring when a short instruction was executed. IR0H was saved into IR0L, and IR0, the lower part of instruction, was being saved when a long instruction occurred. That is, the instruction was saved into IR0. So low of instruction 0 was saved into IR0's low. And the last case was when a long instruction preceded a short instruction, where instruction's higher part was saved to the lower part of IR0L. So that's the possibility, or the three possible cases. And we'll again have a select available. There will be some 2-bit select, some 1-bit select. And finally, for IR0 higher part, either we don't do anything or we save instructions higher bits. So we can have we can either save the higher bits of instruction or we don't save anything. This is not essential, and the last mux is not essential. We can make use of an enable signal to manage this as well. So this is more or less our overall instruction dispatcher, the data path essentially for our instruction dispatcher. Now, how this overall data path is going to work, the control unit, the FSM, will keep a check on what kind of instruction is going to be executed. On the basis of that, the values of select signals will be adjusted. If it's going to be a short instruction, or rather it's going to be the first short instruction, in that case the select 0 will be set to 0, so that short instruction passes, and select 1 will be set to 1, so that IR1H goes into IR1L. Similarly, select 2 goes to 0, so that IR0L moves to IR0H, and similarly select 3 will also be 0, so that higher part of IR0 moves to lower part. So the whole structure that we have already discussed in the previous slide, and here this whole structure will be moved, or will be the main brains through which the FSM will be controlling the overall execution of instruction dispatcher. Coming to the finalized design of our instruction dispatcher, the design contains two registers, IR0 and IR1. Incidentally, we can say it contains 4 registers: IR0L, IR0H, IR1 low, and IR1 high. Moreover, it has 4 muxes: 1, 2, 3, 4 IR0L, H, IR1H, and IR1 low. Similarly, a register multiplexer will be required for selecting either IR1 low or IR1 itself. Apart from that, we are requiring some enable signals specifically for IR0H, which will be saving the higher part of instruction H at times, and at other times it might not be doing anything. We have placed enable signals for all the sub registers. That is, we have 4 enable signals for respective registers and a select line for respective mux as well. Coming to the multiplexer side, the multiplexer side will now be coming to the FSM side. The FSM side will now be containing all of these control signals. The control signals which will be selecting respective muxes, the enable signals for saving data. These will be generated from the state machine. Coming to the FSM part of this example, we'll be designing a mealy based state machine for now. As per our understanding, our first 2 states were merely reading the data from program memory, so that we have data in IR0, we have data in IR1. In order to do that, our first state is 0, which represents empty, that both of the registers are empty. From S0, we will set the read signal to 1 so that the next instruction can be read, and we come to S1. When we come to S1, we mean that IR0 is filled and IR1 is still empty. We move from S1 to S2, and now we say that IR0 and IR1 both have data available in them. Now this read data is not the only signal that has to be set when we move from S0 to S1 or from S1 to S2. We'll be setting a number of other signals as well. In order to understand which signals are to be set, we'll start off with the very first multiplexer. Here at the first time around, we are assuming that IR0 is empty, IR1 is empty, so the data or the instruction coming will be directly saved into IR0, meaning the data the lower part of instruction will be saved into the lower part of IR0. In order to do that, the mux select IR1, let's call it M1 for ease, M2 and M3. So M1 will be equal to 2 because that's the select line that we need to set so that the lower part of the instruction can be saved into IR0. Similarly, we need to set the enable signal to high. So I'll just write it once: IR0L underscore enable will be 1. Similarly, IR0H enable signal will be equal to 0. It should also be equal to 1, so that we save both the values, the lower part and the higher part of the instruction can be saved into respective registers. As far as the rest of the signals are concerned, we can simply say that all other signals can be 0. Because we are not going to save any data into IR1 right now. When we go about the second successive read, again M1 should be equal to 2 and IR0L enable should be equal to 1, IR0 high enable should be equal to 1. Apart from these signals, we need to set the multiplexer lines or the select lines for these 2 multiplexers as well. So let's just see that. We need to save IR0L into IR1L. That is done through M3 being 1. So we can say that M3 is equal to 1. Similarly, for IR1H, to save IR0H, we need to set M2 as 0. Similarly, both the enable signals, IR1 lower and higher, should be enabled as well. So IR1 low enable will be equal to 1 and IR high enable signal will be equal to 1. So these are the 2 cases which we have considered for now. These were the default cases which we need to do so that our overall instruction dispatcher starts working. Now from S2 there are two possibilities. We can either get a long instruction or we can get a short instruction. In case of a short instruction, I'll move on to another state. Let's say we get this information that a short instruction has been received. In that case, the read signal will be 0 this time around. We won't be reading a new instruction. As far as the remaining signals are concerned, first up we start with M3. M3 will now be set to 0 because we need to save IR1H into IR0L, which is placed at 0. And what about M2? About M2 will be saving IR0L, which is available at select line number 2, so M2 will be equal to 2. Similarly, both enable signals for EN1 low and EN1 high should be equal to 1. I'm renaming them just for my ease to save space here. These are the same signals that are referred here. And similarly for M1, now M1 will be equal to 0 because we need to save the content of IR0H into IR0L. So for that we keep it at 0 and we say that enable 0 of low should also be equal to 1. Other than these signals, all the other signals will be equal to 0. Because we don't need to save any data into IR0H, so that will be sent to 0. Coming to S3, again there are two possibilities. Either we have a short instruction or we have a long instruction. But coming back to S2, we have only considered short instruction. In case we get a long instruction, we can get back to S2 in case we get a long instruction. But here, coming back to S2, we need to set read as 1 so that the next instruction can be read. Interestingly, the remaining signals will be more or less same. What remaining signals am I talking about? It's like M1 should be 2, M3 should be 1, M2 should be 0, because we need to save the content of IR0 into IR1 and the content of instruction into IR0. That was already being done when we moved from S1 to S2. So all the signals that we have utilized here when we move from S1 to S2 will be utilized here as well when we have a long instruction. So the remaining, we have the same information here. At S3 we have two possibilities. One possibility is a short instruction. In case we receive a short instruction, we have essentially received two short instructions, meaning it is equivalent to one long instruction, and that means we can go back to S2 in case we receive a short instruction. The output signals will be same as S1 to S2 or S2 to S2. Whereas in case of a long instruction, we move from S3 to S3, and that is done for in case of a long instruction. Here we'll be setting read to 1, and here we are only going to save IR0L into IR1L, so that's going to be done using M3 as 1 and enabling 1 low as 1. Rest all of the signals will be 0 and other signals will be 0. So other signals won't be 0, rather, my bad. Because we have saved IR1 has already been updated, we need to update IR1H by the instruction and IR0L by the instruction as well. So in order to do that, the M2 will be equal to 1 because we need to save the lower part of the instruction into this register, so we set value as 1. As far as M1 is concerned, we need to save the higher part of the instruction into this register. For that we need to set the value of mux as 1 as well. The same goes for the enable signals. Both the enable signals will be set to 1. The remaining enable signal of IR0H will be set to 0. After processing this whole operation, we'll be left off with the IR0 as empty, which S3 is already stating us, because at S2 no register is empty, but at S3 only IR0 H was empty. That was because a short instruction was processed. So this is one of the formulation of FSM, given that we make use of a mealy machine. One signal which I have not considered here was the multiplexer required at the end after IR1. So if I add that multiplexer here, we will have a signal M0, 0 and 1. Sorry. 16 bits of either will be going with 16 bits or will going with the complete IR1. Interestingly, we don't interestingly, we don't need to generate a new signal for M0. M0 can directly be equal to the long or short instruction signal that we already received, which was IR1 of 0, because this was already informing us that whether this is going to be a short instruction or this is going to be a long instruction. If we received 0 at the LSB, it informed us that it's going to be a short instruction. So if this is a short instruction, we'll get M0 as 0. M0 being 0 tells us that we need to pick IR0, the first 16 bits of IR1. So that have been picked successfully. Similarly, if it was going to be a long instruction, IR1 would be 1. The least significant bit of IR1 will be 1. That means we will get M0 as 1. That tells us that we need to pick the whole of IR1, that is 32 bits, and these 32 bits are to be forwarded. So that's why we discarded the signal, though if need be, we can add the signal amongst the output signals generated from the FSM as well, though there is no need for it because it's directly being generated. So this is the state machine for this for this instruction dispatcher. The book deals with a slightly different version of the FSM. Discusses Moore based state machine. That's why you'll see that there are larger number of states. But it doesn't really matter if you design it using a Moore machine or a Mealy machine. Either way, the design is going to be correct, given that it follows all the conditions, all the criteria your system will be in at certain amount of time. So that ends our design question number 2.